Schlemiel. Schlemiel gets a job as a street painter, painting the dotted lines down the middle of the road. On the first day, he takes a can of paint out to the road and finishes 300 yards of the road. "That's pretty good," says his boss. "You're a fast worker," and pays him a kopeck. The next day, Schlemiel only gets 150 yards done. "Well, that's not nearly as good as yesterday, but you're still a fast worker." 150 yards is respectable, and pays him a kopeck. The next day, Schlemiel paints 30 yards of the road. "Only 30, shouts his boss. "That's unacceptable. On the first day you did 10 times that much work. What's going on?" "I can't help it," says Schlemiel. "Every day I get farther and farther away from the paint can." Hello everyone, Aaron here. Welcome back to Leetcode, and today we are doing the increasing order search tree. So let's have a quick read and see what's going on. Given the root of a binary search tree, rearrange the tree in order so that the leftmost node in the tree is now the root of the tree, and every node has no left child and only one right child. So this tree here gets converted into that long chain, right? Basically, we are trying to convert tree into a linked list as if it was read in an in-order traversal. I think this problem would be a great chance to demonstrate good ways and bad ways of doing things. So I'm going to implement first a obvious but slow algorithm, and then we'll have a go at doing something a bit quicker. So I think the obvious first algorithm would be to do an in-order traversal and append those to our linked list, which is a tree where we never use the left node. Let result is null. Let's do... Basically what we want to do is an in-order traversal. Actually, you know what? Let's just code it up that way. In-order traversal of the root, and for each node, actually let's do it for each value. What I want to do is append result value, return result. Now, obviously we need a few helper functions here, but this is generally the algorithm we're going to do. Start with an empty result. For everything in the in-order traversal, append to the result the value. So let's start with the in-order traversal, because we've been doing a lot of tree stuff lately. This one should be fairly straightforward now. This is going to be the root of the tree node, or null. And then there's going to be some f value. I think what this does is it takes a number and will do nothing. And that's kind of what we want to do on this one as well. So I should probably call that null. It's always going to return null. Alright, so in-order traversals, very much like what we've already done in the last couple of problems. So we'll breeze through this a wee bit quickly. Basically, if the root is equal to null, return, we are done. Else, what do we want to do? Actually, these shouldn't be null, these should be undefined. I'm an idiot. Alright, if the root is equal to null, we're going to give up. Otherwise, it's an in-order traversal, so we want to go left, then look at the value, then go on the right. So we want to go in-order traversal of root.left with f. Then we want to apply f to root.val, and then we want to do our in-order traversal of root.right. So that effectively is our Inorder Traversal. This guy here is a higher order function. He's a little bit funky, but basically it's just saying we're going to apply f to every value in the tree. And that thing we want to apply is the append to the result of the value. So let's write our append function. This is going to be the root is a tree node or null, and then I'm going to get a new value, which is going to be a number, and I'm going to return a tree node. Well, there's no chance of it being null, but for consistency, actually, let's keep that option available. If the root is equal to null, return new tree node, which is going to take the value and it's going to have no children. I probably don't need to supply those, but explicit is better than implicit. Technically, it's a Python rule. Well, it's a Python guideline, part of the style guides, but it's a good thing in general to keep in mind. Now, if we're not in the base case, what we want to do is we want to get the new left value is oops, not new left, we're only using new right. I want to append onto root.right val, and then I want to return new tree node, which is root.val null right. All this does is it digs down right as far as it can until it's got nowhere to go, glues a value on the end, and runs back up. So, in theory, all of these pieces are good. Each of them is fairly simple. We'll do a quick check. Basically, increasing BST, if the result is null, we want to do an Inorder Traversal. So we see the 1, the 2, and the 3, and the 4. And for each of those, what we want to do is glue it onto the end of the result. 1 goes on the end, 2 goes on the end of that, 3 goes on the end of that, 4 goes on the end of that, so on and so forth, and we return the result. Quickly check append. If there's nothing to append onto, great, just create the tree node. Otherwise, you've got to go right until you're at the end, at which point you're going to get a new tree node, and then you're going to glue those back together. In the Inorder Traversal, if there's nowhere to go, you're done. Otherwise, you want to go left first, then you want to apply it to the value, then you want to go right. Let's give this a run, and I will warn you, this will probably pass the test cases, but it should not pass the actual. Apparently I have a bad type annotation somewhere. I don't know how to type annotate a higher order function. Let's try wrapping this in parentheses and see what happens. No, it's really unhappy with that. I am just going to leave it unannotated. Wrong answer. Oof. Oh. Hang on. What's going on here? Oh. Didn't actually reassign result. Silly me. Alright, that looks better. So, now we've handled all of the silly problems, let's hopefully see it reject it as too slow. What? This is a bit unexpected. This algorithm I've done here is sometimes called a Schlemiel the painter algorithm. Basically, this append is really slow. It has to walk all the way down. If we go back to the description for a second, when it gets to the end with the 9, it has to go all the way down just to glue the 9 on the end. That's entirely unreasonable. It shouldn't have to do that. What we could do instead is start walking from the right, and rather than append to the end, we what's called cons to the front. So lists in languages like Lisp or Haskell or Camel or all these sort of functional languages, they're defined very much like our tree node is. They are a holding box and a pointer to the next thing. They're called linked lists, and they're very fast to glue things on the front, but they're very slow to glue things on the back. We are constantly gluing things on the back, so we're doing things in the worst possible way. A better way to tackle this would be to glue things on the front, which would mean walking right to left. I think I want to give that a go and see if we can do any better. So how did we go? We did a runtime of 77 milliseconds, 45.2 megabytes. I don't expect the memory to change, but the runtime should come down a lot. This is slow. So we want to do an Inorder Traversal reversed. So now, rather than going down the left-hand side, we want to go down the right-hand side first, and then we want to go down the left-hand side. And now, rather than doing an append, we want to do a cons. So our cons function is a root, which is either a tree node or null, and the value is a number, and we're going to get back a tree node or null. And now, basically, we don't have to do any logic at all. We just want to do val null root. All we're doing is we're adding a new value on the front. We no longer need append. Let's see if this works. Very small change. All we did was flip those two lines and dramatically simplify this function here. But we're inconsistent in our rename. Reverse. God, I can't even spell now. Brain is completely failing. Fingers crossed, fingers crossed. That looks like it's running. Submit. Should be significantly faster than 77 milliseconds, 66 milliseconds. Would you look at that? We knocked a whole 10% off. We even shaved a little bit off the memory usage, although I think that's kind of neither here nor there. But now we are faster than 94% of the TypeScript solutions. So, significantly better solution. We've avoided our Schlemiel the painter algorithm. We're no longer continually walking down to paint the new lines and then walking all the way back up to our paint bucket. We are now carrying the paint bucket with us and walking back up the tree. Right, I think that'll do us for today. Thank you very much for watching, and I will see you all tomorrow. Bye. Only 30.